Stokes' theorem can be regarded as higher dimension of Green's theorem. Stokes' theorem actually says that the line integral f, which is a vector field dot dr, is simply equals to call f dot ds, which can also be written as this: f dot dr equals to double integral divided by d, taking the call of the vector field dot the gradient of small f over norm of f of grad f times this norm of grad f dA. So this is just the basic formula for Stokes' theorem. Now we take a look at an example. The question says evaluate f equals z square I plus y square j plus s vector k and c is a triangle with vertices 1, 0, 0, 0, 1, 0 and 0, 0, 1. So we evaluate this using Stokes' theorem. Solution. First, let's find the call of this function f. So find the call f, which is the same thing as taking the, we can write call f as this. So we have I, j, k. So using vector product, the grad is simply partial s, partial y, and partial z, component wisely on I, j, k. The same thing f, we have z square here. It will be under I component, so we have z square. Likewise y square under j component and x. Now we can now evaluate. So which is the same thing as from vector product, we have plus minus plus. So we have I component here. When we do this guy using those vector product, we have partial y of x minus partial z of y square. So this guy goes. Also j component, we have this and this goes. So we have partial x into x minus partial z into z square plus the k. We fix all these components. We have plus k here into partial s of y square minus partial y of z square, partial y of z square. So we have that. So we can now proceed. When we take derivative of x, which is simply 0 with respect to y, when we take the derivative of y with respect to z, also 0. So everything here is 0 minus j. When we take derivative of x, we have 1. Likewise, when we take derivative of z square, we have minus 2z. If we perform the same operation as we have done with this, so we have here will be 0. Differentiate with respect to y, we have 0 here also. So we are left with minus j into 1 minus 2z, which is the same thing as when we use more the negative sign to open the bracket. We have 2z minus 1 into j component. Therefore, our call of f equals 2z minus 1 j component. So this is just the first step in using Stokes' theorem. So we have done with the call of f. The next thing is to find the gradient of f. After obtaining this, we find the norm, the a, which is ds dy, or in polar form, which is r dr d theta. So let's let P, we let P to be equals 1, 0, 0, and Q equals 0, 0, 0, 1, 0, and R equals 0, 0, 1. We have represented our vertices this with P, Q, and R respectively. So the next thing to do is to find PQ, which is the same thing as Q minus P. So you write Q first, 0, 1, 0 minus 1, 0, 0. So when we subtract component wisely, we obtain 0 minus 1 here, so we have minus 1, 1 minus 0, and 0. So that's for PQ. And for PR, we have R minus P. So we have 0, 0, 1 minus P, which is 1, 0, 0. So we have minus 1, 0, 1. So now the next thing to do is to take the cross product of PQ and PR. So doing that, we obtain the PQ PR, cross product of it we have IJK. For PQ we have minus 1, 1, 0. So we have minus 1, 1, 0. And for PR we have this, we have minus 1, 0, 1. So continue with this process. We have I into this and this, we're going to fix this. So 1, this guy will just be 0. So minus J. We fix the first row, second column, we have minus 1, minus 0, plus K. First row, third column, we have 0 plus 1. So which is the same thing as I plus J plus K. These are just unit vectors, which can also be written as 1, 1, 1. So our PQR is simply this. So now next thing to do is to recall our equation of a plane. This Stokes theorem is kind of tricky sometimes. It involves some step-by-step process. So equation of a plane. So recall equation of a plane. Equation of a plane. So it says A into S minus S naught plus B into Y minus Y naught plus C into Z minus Z naught equals 0. So PQPR, we let it to be A, B, C. So you can plug in all those values here. And S naught, Y naught, Z naught, you can just fix any point here. You can either take this, or this. So let's take the first one, which is P, 1, 0, 0. So we have, let's write it here. We have S naught, Y naught, Z naught. So we can now plug into our equation of a plane. So here is 1, we have 1 here. S naught is simply 1 plus B, which is 1, and Y naught is 0 plus 1 into Z minus 0. So which is simply S minus 1 plus Y plus Z equals 0. So we have S plus Y plus Z equals to 1. So now we can now use our equation of a plane that we obtain here. Let's represent it with F. Let F equals S plus Y plus Z minus 1. So observing from the Stokes theorem formula, grad F over norm of F times norm of F, this guy it goes, That's it cancels each other. So we take the gradient of f. Don't forget that this is dot product. We take the gradient of f, so we have, since we have obtained f here, grad f is simply taking partial s, partial y, partial z times this function, which is s plus y plus z minus 1. So when we do this, when we differentiate with respect to x first, when we use this guy to multiply this by differentiate with respect to x, we obtain 1, comma, differentiate with respect to y, this will be 1. All these guys, they are just constant to the family, so we have 1 also here. The same thing with 0, we have 1. So our grad f is simply 1, 1, 1. So the next thing to do now is to obtain our limit of integrations. So now, when we consider this, when we set y, z equals to 0 on x-axis, let's say we have, let me write it here, s plus y plus z equals to 1. When y equals z equals 0, what happens to this guy? This will be 0, 0. So we have s equals to 1. So x lies between 0 and 1. Likewise on xy plane, z will be 0 on xy plane. So this guy is going to be 0 on xy plane. Sy, let me write it like this, xy plane, so z is 0 on xy plane. So since z is 0, s plus y equals 1, in which y equals to 1 minus x, that is, y is between 0 and 1 minus x. So we are going to use this limit of integration to evaluate our integral. So now, we evaluate our integral. So the line integral, we have f dot dr equals limit of integration. We plug in all this value we obtain here. So the first one is 0 to 1 and 0 to 1 minus x. Our call f is simply 2z minus 1 times get component. So we have 2z minus 1 times get component dot the gradient of f, which is grad f. We have 1, 1, 1. When we take the norm of this, actually, after taking the norm of it, it will cancel each other. So there's no need of doing that extra work. So we have dA. The next thing is dA. dA is simply ds dy. So we have dy ds here. Since we have to evaluate with respect to integrate with respect to y first. So now, this is in components form. So taking the dot product, we are going to have 0 to 1, 0 to 1. Having that, we have 0 to 1 minus x. Taking the dot product, we have 2z minus 1 dy ds. But recall that z equals to 0 on x-axis. Also, on xy plane, we have z to be 0. So this guy is simply 0. When you plug in z here, that will be 2 times 0, that's 0. So we just have 0 to 1, 0 to 1 and 0 to 1 minus x into minus 1 dy ds. So we can now integrate. Doing so, we have 0 to 1, 0 to 1, and we have when we take this respect to y, we have minus y. converting from 0 to 1 minus x, and the rest remains. So now we plug in our values here. We have 0 to 1 into minus 1 minus x ds. This we find when we plug in 0 in. So the next thing is to integrate with respect to x. We have minus outside, we have x minus s squared over 2, 0 to 1. Now we open this bracket, we have okay, we can just plug in directly. We have 1 minus half. By plugging 0, that will just vanish and everything goes away. So which is simply minus into half. So which is our final answer, as well as minus half. So that's the solution for the Stokes theorem. You can review the question again, the solution to the question again, if you have any kind of maybe sort of issue understanding it. Thanks for watching. Minus half.